Hello. Yeah, I meant to make a video, but I forgot. So, for me, recursion is best understood through examples. Just seeing the code and kind of getting a sort of a basic framework or structure in my mind. So, one of the first things that I'm thinking about or trying to define when I'm doing recursion is like what the base case is. Like, what's the most simple, smallest, maybe. Um, case or example I might have in this situation. So in the case of factorial, the smallest example I could think of is, well, 0 factorial, right? Although here it says given n of 1 or more. So so then that would be 1. So 1 factorial would be the smallest factorial I could have. And so a lot of times that defines your base case right there. So if n equals, if n equals 1 is the base case, right? The smallest case I could have. Well, what would the value be if n is 1? And they're showing me in the example, but I should also know that 1 factorial is 1, right? So if n equals 1, I'm going to return 1. Okay, so now the next question is, do I need to have more base cases, right? Sometimes there might be more base cases. Or do the rest of the cases sort of build off of that first base case? And in this case, I'm using the word case a lot. But in this situation, everything does sort of build off of that first base case, and all I want to do is just multiply. For example, in the case of 2, I would just multiply what n is at the time times 1 factorial. Like that's the way factorial works, right? It's like 2 times 1 factorial. 3 factorial is 3 times 2 factorial, right? So it's a beautiful example of recursion, right? So basically, in all other cases, I'm going to return n times whatever the previous factorial was, right? It's like it is like a recursive definition, really, right? Boom, and that should work. I think, yeah, bang, that works, right? And then yeah, to step through that, we'll talk about that later. Bunny ears. So bunny ears, once again, count the number of ears on my bunnies. The base case would be having no bunnies. So that's bunnies equals 0 would be the base case, and therefore I have 0 ears, right? And the question is, well, is 1 sort of a unique case, or does it essentially build the same way 2 builds and all that good stuff? And basically, yeah, every time I get a bunny, I get 2 more ears, right? So whatever the result of the previous bunny ears is, I'm just going to add 2 to it, right, every time. And yeah, that may be a nice way to sort of look at or think about recursion at this point. But like, yeah, if I knew how many bunny ears I had with 5 bunnies, if I have 6 bunnies, it's going to be 2 plus however many bunny ears I had with 5 bunnies, right? Well, how many bunny ears does 5 bunnies has? Well, it's 2 more than 4 bunny ears, and 4 bunny ears is 2 more than 3 bunny ears, right? And that's the way this recursion thing is working for us, right? So great, simple, as about as basic as you get with recursion. You kind of get the idea. Now you look at Fibonacci, and Fibonacci is actually, again, a great time to use recursion. It's pretty hard to define this, or a little harder to define this without recursion. But here's the thing that makes this kind of a unique, sort of tricky problem is that there's 2 base cases, and they do tell you up top essentially 2 base cases. But yeah, I would think of it as 2 base cases. So if n equals 0, I want to return 1, okay? And the other base case is if n equals 1, I want to return 1. Now you may be, or I'm sorry, that should have been 0 up there, but you may be kind of saying to yourself, well, how do I know, that something should be a base case or not be a base case? And I think one way to have like a pretty strong idea that something should be a base case is that it doesn't really follow the rules of the rest of the cases, Like, for example, in the case of 0, n being 0, or n being 1, I really can't add the 2 previous numbers together because there aren't 2 previous numbers, So once I get to this point, I can essentially add 2 previous numbers together, right? And so that would be a good time to think, well, what happens in the case of n being 2, right? What happens in the case of n being 2? What do I want to return? Well, I really want to return Fibonacci of 1 and Fibonacci of 0, right? Added together, right? And that's really the way this thing is going to work. So I'm going to take Fibonacci. It might be, might seem weird that I'm saying n minus 2, but I don't know, not really matters. Bottom line is I'm going to take the one before, I could say n minus 1, the one before, and then the one 2 values before it, you know. What did I do? What did I do? Spell line 4. Fibonacci, it's right there. Oh, I'm using. I got you. I got you. All right. Boom. Okay, so that's a little special. It's a little special because think about it. I have not only do I have 2 base cases, but I actually have 2 calls on the same line. 2 calls to the same function on the same line. So, oh, okay, that's a thing. I can actually do that. That's going to happen sometimes. And then finally, bunny ears 2 is also interesting because it sort of injects this idea of if statements. So it is similar to bunny ears, right? Where if bunnies is equal to 0, I will return 0. But now it gets to this point where I have 2 sort of different things I'd like to do. And that's, again, it's something we didn't see in the 2 base examples we showed earlier. But if the number of bunnies is odd, I think I do something different, right? What do I do? The odd bunnies have 2 ears. Okay. So let's say if we'll define this as the ears being odd, right? And so they have the normal 2 ears. So what I'm going to do, I'm going to return 2 plus bunny ears 2 with bunnies minus 1. Okay, so that's kind of the classic. That's the classic, right? Now, do I need another if statement here to define even? Do I need another if statement here to define even? I'm going to argue no. I do not need another if statement to define even because if it's not odd, it's got to be even. Well, what happens when it's even? I have essentially an extra ear, right? 3 ears. So instead of returning 2, I'll return 3 plus bunny ears. And let's see how that works. What happens? I did not spell it right again. Okay. All right, and so that's an interesting one. It's an interesting one because you can put an if statement and then sort of decide what you do, so you can have some branching within this code as well. And again, that's why and how sort of recursion can be used to accomplish anything that you could with a for loop or something like that, because ultimately you can make decisions before you call the function again. So hopefully that's a little bit helpful. And again, I think the more examples you see, the more the more practice you get, the more it'll make sense, I guess.